Hello everyone, I'm Pengze Zhang from Xiaohua University. It is a great honor for me to be here to introduce our recent work, Formulating Discrete Probability Flow through Optimal Transport. This work was done during my internship at WeChat. In this work, we studied the theory of discrete diffusion models. We begin by reviewing two common diffusion models, continuous diffusion models and discrete diffusion models. Subsequently, we introduced a discrete probability flow based on the optimal transport theory. And finally, we experimentally validated our theory. First, let's explore these two diffusion models. The continuous diffusion model treats the diffusion process as a continuous noise injection process. This model has been mature research. For example, for SDE, it can sample the entire data distribution from an initial point. And in the case of ODE, data generation and initial points are uniquely related, ensuring the controllability of the diffusion model. In contrast, discrete models view the diffusion process as discrete state transitions. Current methods like SDDM are similar to SDEs, which can sample from a single point to generate the whole data space. Therefore, we point the question, how can we reduce this uncertainty and design a discrete probability flow? In this paper, we have the following contributions. First, we prove that the continuous probability flow is the most optimal transport met under certain conditions. Then we propose a discrete probability flow (DPF) under the framework of optimal transport. Finally, we propose a novel sampling method based on DPF, significantly decrease the uncertainty of the sampling outcomes. Now, let's focus on the discrete diffusion model. The discrete diffusion model is based on Kolmogorov differential equations for state transitions. Common transition metrics, as shown here, allowing neighborhood states to transition between each other. We observe that such a process exhibits mutual flow, where state I can transition to state J, and J can also transition back to I. Consequently, such a process is certainly not optimal transport, as it is characterized by substantial uncertainty. To tackle these issues, we propose a novel transition matrix, as illustrated here. It's evidence that by incorporating a ReLU operation, we ensure that high probabilities can only transition towards low probabilities, effectively mitigating mutual flow. Based on the proposed method, we validate the following two propositions. Proposition 5 confirms that our proposed generation process shares the same marginal probability distribution as the original process using Q. Consequently, there's no need for retraining. Proposition 6 verifies that our proposed method constitutes the optimal transport for the original process generated by Q. In this way, we can calculate the reverse transition rate and generate samples using Euler's method. Let's move on to the experiments. We first evaluate our method on trial dataset. As shown in table, the data generated by our method have superior certainty than existing method SDDM. Moreover, we also visualize these results. We can find that when sampling from the same initial points, SDDM can cover the entire data space, whereas our method samples are concentrated in a few regions, exhibiting greater certainty. In addition, we employ our DPF on CIFAR-10 dataset. As shown in table, our method sample results have a smaller standard deviation. Here is the visualization results on CIFAR-10. It's evidence that, starting from the same initial points as T, our DR method produces a variety of images with different content. In contrast, our generated images exhibit consistent content, indicating a reduction of uncertainty. This concludes my presentation. For more details, please visit our GitHub. Thank you.